Hello, everybody. Thank you for joining us today. You are part of the 360 people worldwide who have registered to view this webcast powered by Yole Développement and clearly dedicated to micro-LED display. My name is Camille Verrier, and I am Marketing and Communication Project Manager for Yole Développement. Before we get started with the webcast, I would like to give you some information regarding the logistics. So you have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for the remaining questions, we will make a follow-up via email within a week. Concerning the materials and content, please note that the presentation is available and downloadable in the materials section. You will receive also an email after the webcast and within 24 hours with a link to the recorded session. Today, Eric Viret, Senior Analyst from Yole Développement, will share his analysis and provide an overview of micro-LED display technologies, key benefits and drawbacks, technology challenges, industry landscape, and market opportunity. Eric, the floor is yours.
Thank you, Camille. Thank you for the introduction, and thank you, everybody, for joining us today for this webcast. I will, of course, start with a brief introduction of Yole Développement. I'm assuming that most of you are probably familiar with the company, so I will go fast. Yole is a market research and consulting company with more than 30 analysts operating in a variety of fields, as you can see on this slide. We are probably most known for the off-the-shelf report, but that's really just the tip of the iceberg. We have a lot of many other activities, and we do a lot of consulting and analysis and custom one-to-one report and consulting actions. Also involved in financial services, such as merger and acquisition, due diligence, both on the buy side and the sell side. Yole is organized as a group of companies, so Yole Développement is the main company, but you have sisters companies or subsidiaries such as Yole Finance, Blue Morpho, System Plus Consulting that helps us with reverse costing, cost analysis, and reverse engineering, as well as Nomad, also our IP analysis expert. Everything you're going to hear today is part of our recently published micro-LED display report. As you can see, we have many other reports in connection with the display industry, upcoming reports on quantum dots and augmented reality, virtual reality, and mixed reality displays. As I mentioned, our sister company, System Plus Consulting, also has a lot of cost modeling tools. Some of them are available for purchase. Some are just for internal use, for our internal analysis. So if you have any inquiries in this field, do not hesitate to contact them. Okay, so now that we are done with the shameless self-promotion, let's get into today's topic and start by describing a little bit what micro-LED displays are. I'm assuming that some of you are display experts, but some probably come from other industries. So without going into too much detail, I thought it would probably be a good start to explain a little bit the fundamental differences between LCD technologies and EMISSIVE technologies, EMISSIVE displays. So LCDs, which is by far the dominant display technologies on the consumer market. In an LCD, you can see the structure here, and starting from the bottom, you have a backlight unit that typically composed of a matrix of LEDs, could be anywhere between a handful to a few hundred. And those LEDs generate a uniform light that then goes through a matrix of millions of small light switches constituted by the liquid crystal. So each of those switches can be individually controlled by a matrix of transistors, the TFT backplane. And they can be controlled so as to block the light or transmit the light and transmit it through a set of patterned red, green, and blue color filters, which constitute the individual subpixels. So as you can see, it's a pretty complex structure. And in the end, we are lucky that LEDs are very efficient light sources because optically, it's a pretty inefficient design, and most of the light is wasted into the LCD stack, either blocked by the LCD or blocked by the color filters. So overall, an optical efficiency that's pretty low, around 5–10%. By contrast, if we look at the emissive display structure on the bottom, in an emissive display, each subpixel is a tiny light emitter, which generates its own light and which brightness can be individually controlled, again, by a matrix of transistor. So if this light emitter, in this case OLED is by far the most widespread emissive display technology. If this light emitter is efficient, the overall display efficiency can be fairly high because we don't have all this complex optical stack that blocks the light in many locations. Another benefit is that you can control perfectly and completely turn off each individual pixel, which means you can have real absolute black, for opposition to LCD displays where you always have a little bit of light leaking through those light switches, the liquid crystal. So as I mentioned, the most common emissive display technology is by far OLED. Probably more than 20% of smartphones now use OLED displays, and it will be way above 50% in just probably about 3 years by the end of the decade. They're just getting started in TV as well, market dominated by LG displays so far. So in OLED, OLED stands for organic LEDs. The emitting layers, which are organic materials, can be coated and patterned over very large areas and directly on top of the TFT backplane. So those displays are manufactured at the square meter scale. If you look, for example, at Samsung, which has probably more than 99% of the OLED display market for smartphone, they typically operate in generation 6 fabs, which means that they're processing substrates, display substrate that are close to 3 square meters. And LG, which is the leader in TV, using a slightly different technologies, but still OLED, I think they're currently building a generation 10.5 fab, which means substrates that are more than 10 square meters. So micro-LED displays are very similar in OLED in the sense that they are also an emissive technology. Each pixel is a tiny LED chip which brightness can be individually controlled. But the emitting material is of a different nature. It's an inorganic material. Some people call those iLED for opposition to OLED. The challenge with those materials is that there's no technology to deposit blanket layers over very large surface. So typically the LEDs are manufactured on 4-inch to 6-inch diameter wafers. So the art of making a micro-LED display consists in processing those LED wafers into either individual chips or small arrays of micro-LEDs, which can then be picked up, transferred, and assembled onto the backplane. So why do that? It seems intrinsically more complex than OLED, but inorganic LEDs have some benefits over OLED. They tend to be much brighter, much more efficient, and they're also much more robust. So in terms of display performance, this translates into potentially a lot of benefits. First of all, the power consumption. Overall, you basically get the best of OLED and LCD together. So I just mentioned highly efficient emitters, which translates into low power consumption. And this is always desirable, but especially for mobile devices because it significantly increases the battery life. As I mentioned also, you can completely turn the pixel off, which means you have a perfect black. But LEDs are also very, very high brightness. Actually, I did a back of the envelope calculation. If you were to build, let's say, a cell phone display with 400 pixels per inch and do that using a 10 micron by 10 micron LEDs, if you drive the display close to the peak efficiency of the LED, you would easily get a brightness that exceeds 100,000 nits. So this is more than 100 times than the best cell phone displays currently. If you drive them a little bit harder, you can probably reach 300,000–400,000 nits. Of course, nobody needs that kind of brightness on the consumer display, but it shows you that you can push the brightness very high, and because you also have perfect black, it means that overall you can achieve a very high dynamic range, very, very high contrast, which is very important in the new generation of displays and especially in TV. LEDs are also narrowband emitters, which means that you can achieve a very wide color gamut, at least clearly wider than OLEDs. I also mentioned they are very robust, so they have a long lifetime, environmental stability. They can operate in a very broad range of temperature. You can achieve fairly high resolution, pixel density. I think the company Ostendo in California demonstrated a micro-LED, micro-display with pixel density up to 5,000 ppi, pixel per inch. You can also deliver fast refresh rate, wide viewing angles, which are two of probably the most vexing limitations for LCD displays. You can also produce those micro-LED displays on curved or even flexible backplane. And you also have the possibility in some design to integrate additional electronic in between the pixels directly into the front plane, directly into the display structure. An example of those could be a fingerprint reader or a motion sensor, gesture recognition system. So that opens the door for displays with added functionalities. So this is it. I guess this is the end of the webcast. Thanks for joining us today. We do have the best display technology ever. Unfortunately, it's not that simple, and of course there are some challenges associated with the manufacturing of those micro-LEDs. I would say that the science is here, but the concept is already fully validated. Prototypes have been demonstrated, but micro-LEDs, as you started to understand, are inherently complex. So to achieve volume production at costs that are compatible with the application, there's still many engineering and manufacturing challenges that need to be resolved. So I'm just going to go through a few of them. First, the idea of using LEDs in an emissive display is not new. We're actually already pretty much surrounded by those in those large billboard video displays that we find either along the freeways or in the malls, in the stadiums, or on some building facades. So in those displays, the individual pixels are constituted by packaged LEDs that are containing red, green, and blue chips to form the individual pixel. But typically, the pitch and the space between each pixel is in a range of a few millimeters to a few centimeters. The highest resolution now are probably around 1 millimeter. So what we are trying to do with micro-LED is an order or 2 orders of magnitude smaller. Here on this slide, I'm representing the spacing between subpixels versus the pixel density. Starting from the top left, you can see, for example, a TV, which has a pixel density of about 80. For a 4K TV, 55-inch, you have about 80 pixels per inch. And this translates into a space between individual pixels that's about 100 microns. For a cell phone at 500 pixels per inch, the space between the pixels drops to less than 20 microns. I've represented consumer virtual reality devices. In the consumer products available today, I represented here the Oculus Rift and the HTC Vive, but it's the same for the Samsung Gear VR, the Sony, and so on. Currently, they're around 500 ppi, less than 500 ppi. I represented here at anywhere between 1,000 and 1,500 because that's really a goal that the manufacturers need to achieve, I would say, as soon as possible, because right now the resolution, the pixel density of those displays is not sufficient. Actually, if you do the calculation, the ideal pixel density would be closer to 3,000. And then all the way to the right, you have those micro displays, which can be used in augmented reality, mixed reality devices with pixel densities in excess of 2,000, 3,000, and up to 5,000, as I mentioned earlier. So when the pixel density is that high, the spacing between each pixel is only, actually the pitch of each subpixel is only a few microns, 2, 3 microns. Which means that it's starting to get close to the density of the micro-LEDs on the wafers, on the AP wafers. So in that case, what you can do is just cut an area of the wafer that corresponds to the size of the micro-display and directly try to either hybridize, connect this matrix of micro-LED onto the transistor matrix. In this case, it's typically going to be a CMOS silicon type of circuit. Or you can also try to grow directly the transistor structure, the TFT structure, on top of the LED. But if you have a lower display pixel density, then the density of the pixel on the substrate and the density of the pixel on the display don't match. Excuse me. So this means that you have to somehow find a way to pick up each individual micro-LED on the wafer and disperse them or spread them onto the surface of the TFT substrate. So this is a first issue, because if we start looking, for example, at making a 4K display, we're talking about 25 million subpixels, 25 million micro-LED chip. Typical LED pick-and-place equipment today delivers about 25,000 units per hour, which means that if you're trying to make a TV with standard pick-and-place equipment, it's going to take about 41 days to make a single TV. So obviously we have a problem here, something that's not very economical and practical. So there is a need to develop transfer technologies that can handle hundreds of thousands of chips together. So this is what we call a massively parallel pick-and-place. So the idea is very similar to traditional pick-and-place, except that you manipulate thousands or hundreds of thousands of chips at the same time. So as you can see here, the pitch on the pickup array is an integer multip of the donor array and matches that of the receiving display backplane. But it's pretty complicated. There's a lot of challenges associated to that. You want to be able to singulate the dies, but also keep them in position so they don't tip or fall from the donor wafer. Yet you need the pickup head to exert enough force on the die to detach them from the donor wafer. And then you need a mechanism to release them on the backplane so they stay in place and they are connected, hybridized to the backplane. So it all seems pretty complicated, and it is. But the good news is that a lot of companies are working on those issues. We've done a pretty thorough patent search and analysis, and there's a surprisingly large amount of companies that have come up with a lot of pretty different solutions. There's a phenomenal amount of creativity here to find solutions to those problems. So we've seen a wide variety of technologies being developed to solve all those problems. It's probably a bit too early to pick a winner, but you have a lot of different holding mechanisms. Could be thermoset adhesives, sticky films, metal solders, mechanical post with breakable tethers and anchors. We have release mechanisms that could be thermal or assisted by lasers, and coupled for the pickup array or the pickup stand, coupled with electrostatic, magnetic, or electromagnetic forces. So a lot of different combinations, and clearly a lot of progress are being made on those technologies. And, I'm not even discussing here pickup technology, transfer technology that I qualify as semi-continuous process, more akin to a flexographic printing process or fluidic assembly. So clearly a lot of work being done, but a lot of solutions being developed, and pretty exciting and fairly new field. Another issue with micro-LED is the efficiency. I mentioned earlier that LEDs are very efficient light source, and it's the case for traditional LEDs, so large dimension LEDs, where you have an external quantum efficiencies of up to 70% for blue LEDs. Unfortunately, with micro-LEDs, the efficiency drops significantly, and the main reason is that at this scale, you have a sidewall effect. The defect on the sidewall, they can be contamination, open bonds, or structural damages created by the manufacturing process, the singulation process. All those defects are negatively impacting the efficiency of the LED, and their impact can extend through a few microns into the bulk structure of the micro-LED. So if you have a device that is more than a few hundred microns wide, this is not much of a problem. But on a device that is 10 micron or less, the sidewall effects become very significant. Without getting into too much detail, this is also compounded by the fact that even at low efficiencies, those micro-LED are still so bright that they have to be operated at fairly low current density, way below the traditional peak efficiency in traditional regions where LEDs are driven. And in this low current regimes, typically those defects, sidewall defects, tend to dominate because you cannot saturate them completely with carrier. So significant challenge, because if you really want to deliver on the power consumption promises of micro-LED, you definitely need to solve this issue and improve the efficiency to at least above 50%. But once again, there's a lot of companies working on this, and some very significant progress have been achieved. We've had companies reporting already micro-LED less than 5 micron size with efficiencies above 50%. It's all about the chip architecture. You can devise a lot of trick in your chip structure in order to reduce the effect of the sidewall defects, but you can also work on the manufacturing process, of course, to eliminate those defects or avoid their formation. Another interesting route that's explored by various companies is the use of nanowire or micro wires. Those are, in a sense, 3D LED microstructures that allow you to eliminate or reduce the sidewall defects. So here, to be more specific, a micro LED is not necessarily made of micro or nano wires, but micro and nano wires could be an interesting way to make micro LEDs. And we have companies such as Aledia or Glow that are working on this strategy. Another significant challenge for micro LED displays is defect management. Nowadays, most high-end displays are guaranteed with 0 defects, so every single pixel and subpixel is functioning. If you look at manufacturing yields for micro LED display, if we simplify, we have 2 major contributors here. You have the chip yield itself, and then the transfer yield. So if a die is not properly picked or placed, or if you have a faulty connection, then you're going to have a dead pixel or a missing pixel, which is already unacceptable. So as you can see below, even if you achieve very high yields, you still have about a few parts per million defects, which, as I just mentioned, is already unacceptable. So no matter how good you are at improving your yield, you need a defect management strategy. And there's not a lot of options here. It's basically, you're capable of identifying and repairing each individual defective pixel before shipping the displays, or you can use a systematic redundancy and say, okay, I'm going to use 2 subpixels, 2 emitters for each subpixel, and hope that at least one of the 2 will be operating. So the best strategy is really dependent on the application, and also probably dependent on the toolbox that you have at your disposal. Obviously, a systematic redundancy is going to double the pixel and the initial pick and place cost. The question to ask is, can this added cost be offset by the saving that results from not having to do all the additional transfer cycle needed to repair individual defective pixels? And if you want to repair pixels, it also means that you have a good way to test them. The testing is also a potential significant roadblock here, because you want to be able to test very efficiently, very rapidly, and ideally to test without having to wait for the pixel to be fully assembled, because if you do so, whenever you replace a pixel, you need to somehow reconfigure, reroute the electrodes, and this can be pretty complicated. So defect management, definitely another thrust area, another issue in micro-LED manufacturing. And there are many more challenges. I don't have time to go through everything today, but as you can see on this graph, color conversion can also be an issue if you're not using red, green, and blue LED, but choose instead to use just blue LED with a color converter, light extraction, beam shaping, and so on. The last topic I want to discuss today on those challenges for micro-LED is probably the supply chain. So as you can see here, enabling high-scale, high-volume micro-LED display manufacturing means bringing together some pretty disparate pieces of technologies and different industries. It starts with the LED makers, and what LED makers traditionally do well is LED epitaxy on 4-inch to 6-inch wafer. And for the traditional LEDs, which are hundreds of microns wide, if not millimeter wide, a clean room class 10,000 is plenty enough. Actually, as a matter of fact, many LED makers operate in even less clean environment, class 100,000, or if not a million. The lithography resolution is not too demanding on traditional LED. You can get away with a mask aligner, which is a fairly cost-efficient lithography technology. Delivers resolution of a few microns and overlay of a few microns. For micro-LED, obviously, you're operating at different scales. You have devices that could be less than 10 or less than 5 microns, and you have features on those devices that are probably going to require lithography resolution of at least 1 micron, if not better than 1 micron. And what that means is that to enter this market, to supply this market, LED manufacturers will probably have to essentially build a new fab in a much cleaner clean room, and probably with completely different and new lithography equipment, probably moving from those mask aligners to steppers. And obviously, all that has a significant cost, and I'm not sure any LED makers right now is in the position or willing to make such an investment for a market that is still uncertain. Of course, there are alternatives, because those lithographies, those clean rooms, they already exist, and a lot of semiconductor foundries have a lot of available capacity. So one solution here could be to have, for example, a LED maker partner with a semiconductor foundry to use this existing capacity, lithography tools, and avoid to duplicate the capex. The other major brick into this micro-LED supply chain is the display maker. Today, they are vertically integrated in the sense that they manufacture the TFT backplane and the front plane, and they deliver fully functioning panels to the OEM. They're obviously going to struggle not to become just a component supplier, because they could lose the control of the front plane, and I don't think those display makers want to become just a TFT backplane supplier to whoever is going to make the final assembly. And then you have the missing links, those mass transfer assembly technologies that I mentioned earlier, which are they do exist in a lab in small scale. Some prototypes have been built, but there's no off-the-shelf equipment yet. And I'm talking about the transfer equipment, but it's also true for the test and equipment, the repair equipment you use. Typically going to use a laser repair tool that allow you to cut traces or weld traces to repair the pixels. And all those technologies exist with standard displays, but they will need to be adapted, adjusted for micro-LED. So in the end, you have a supply chain that's pretty complex and lengthy compared to that of traditional displays. And each process is critical, and managing every aspect effectively will be challenging. We believe that as of today, no single player is in a position to solve all those issues, and it seems unlikely that, at least in the short term, any will be able to fully vertically integrate, as it's not for very high volume production. So in the short term, we believe that only a highly motivated OEM could have the leverage and financial means to bring those elements together and enable high volume consumer applications. So here we show an example. It's only one example of a possible supply chain. There are many other possibilities. So in this scenario, the display maker would invest in transfer equipment and technology, manufacture the TFT backplane, outsource the micro-LED processed epi wafers, and do the assembly of the final display for the OEM. But you can imagine a lot of different supply chain. For example, the assembly could be performed by an OSAT, or the OEM maybe could even decide to do the whole thing if it's a small enough market, small enough capacity needed. So who are the key player in this market? Obviously, we don't have an industry, we don't have supply chain yet, and we don't have any product on the market. So in that case, a good way to see who's playing in the field is to look at patent activities. Those of you that are familiar with patent research probably know that formulating the search equation is a tricky and critical step to any patent landscape analysis. If you're too vague in your keyword and search structure, you get quickly overwhelmed by thousands and thousands of patents that you have to sift through manually to identify the relevant one. But if you're too precise or restrictive in your search, in your keyword, you're going to miss a lot of patents. Especially some companies are purposingly using very vague terms because they want the protection, but they don't want the visibility. So they're kind of trying to evade searches. And so we've found a lot of patents where LED, for example, is referred to as an optoelectronic device or a semiconductor device, and the display is called an information device, and so on. So in the end, there's still a little bit of manual work, but we identified about 1,600 patents that we consider relevant to the field of micro-LED displays. As you can see, the activity started around 2000, really picked up around 2010, and there's another surge probably around 2014, which corresponds to the year when Apple acquired micro-LED display startup LuxView. The drop you're seeing for 2015 and 16 is just an artifact. It's related to the fact that it takes up to 18 months and sometimes more between the time the patent application is filed and the time the patent is published. So this drop you're seeing here is just related to the fact that we conducted this search a few months ago, and all the 2015 and 16 patents hadn't been published yet. So once you have this corpus of patents, you can start doing your analysis. And when you start doing the analysis by company and by technology node, trying to figure out who's working on what, whether it's chip structure, efficiency, transfer process, color conversion, and so on, it becomes clear that LuxView/Apple now as by far the single largest and broadest IP portfolio on the topic. They really cover all the major thrust areas. But what's also interesting is to see the diversity of the companies that are operating in the field. We have many startups, EMISSIVE, Yole, PlayNitride, Lumiode, InfiniLED, which was acquired last year by Oculus / Facebook. You also have a lot of display makers. Sony was probably one of the most visible, but also Sharp, AU, BOE, CSOT. You have the LED makers, and you also have a lot of semiconductor companies, Intel, for example, various OEMs. So a very broad field, and the question is, will anybody have a full freedom to operate? Will anybody have a patent toolbox that covers all the key essential elements? And it's pretty likely that if this micro-LED display opportunity ever materialize, we're going to see a lot of licensing, cross-licensing, and litigation activity. Moving now to the the application. Here, I want to show you that, as I mentioned, there's no commercial product yet on the market, but just to confirm that micro-LED displays are real, at least we've seen some prototypes. I think the first prime time exposure for micro-LED display was at the CES 2012 when Sony showed this this prototype of a full HD TV based on micro-LEDs. It was never seen again for the reason that you probably started to understand now. But yet it really gathered rave reviews from the people who were able to work on the booth. There is a commercial product. I personally don't like to call it micro-LED displays. So it's a large video display similar to those billboards I mentioned earlier. A large video display that is made of micro-LED, so it fits the definition in terms of the size of the chips, because each sub-pixel is constituted of 30 by 30 micron size LED chips. That said, the pitch is fairly high, above 1 millimeter, and in my definition, it doesn't really deserve to be called a micro-LED display. But at least it shows the ability that the company has to manufacture and manipulate a very small LED chip and use them for a display application. So the question, of course, is how do we forecast? How do we make forecast on the technology that doesn't exist yet? So the first step, obviously, is to do what we just did: is do a thorough analysis of the technology, try to understand what could be the potential benefits and the potential drawbacks or limitations of micro-LEDs. Make sure we understand where we stand in terms of the technologies, what are the challenges, the technology nodes, what are the paths to resolve the different problems, how far we are, what could be a time roadmap to resolve all those problems. And then you put all that together, and on the other side, you put your list of potential applications, the different segments, TV, cell phone, wearable, micro displays, and so on. And for each of them, you look at what are the performance requirements, the technology requirements, the cost target, what are the incumbent technologies, what do they do, what do they don't do well, and so on. And then you have this multidimensional grid analysis that allows you to conduct a SWOT analysis for each application. And from there, you can define a roadmap for each application and build different scenarios. So it's a complex process. Again, we don't have a crystal ball, but I would say we are making very educated guesses, and this is completed by a lot of interviews that we conduct with industry players at different levels of the supply chain to get a feel really of where we are, what it is that they are working on, what it is that they believe in, what do they think would be the most challenging applications, and so on. So I won't go through all applications. I just want to emphasize two applications. The first one is the smartwatch or other wearables. We really see those as the low-hanging fruit for micro-LED displays. Multiple reasons for that. The first one is cost-wise. On a smartwatch, you have a very low pixel count, less than 500,000 pixels. So that compares to a 4K TV at 25 million subpixels. So low pixel count, so this translates into a fairly low epitaxy cost that's compatible with the application. It means that you can also have a systematic pixel redundancy and still be cost compatible. There's a fairly high pixel density, which makes the transfer process fairly efficient. You could probably populate a smartwatch in just a few pick and place operation, probably in around a minute or maybe even less. So you have a lot of, in terms of the technology, we're pretty close. You can use a fairly large LED, 10, 15 microns, which means you don't need to, you're not struggling as much with the low efficiency for the very small LEDs. In terms of performance, you have something that's potentially very differentiating for wearable, especially with the low power consumption, which could significantly increase the battery lifetime. And then in terms of the supply chain, it's not too strenuous in the supply chain. The volumes are fairly low. It doesn't take that many MOCVD to make a large amount of smartwatches. So we see this application is probably a good way to establish a small case supply chain and test drive the technology, perfect it, and set the stage to bring it to the next level, where maybe it could start addressing other applications. So obviously, what we have in mind here with the smartwatch is Apple, so we don't know yet what their plans are, what they're going to do, and when. It's not in Apple's culture to do manufacturing, but for this application, if they wanted to, it wouldn't be too far-fetched to imagine that they could handle some of the manufacturing themselves. As I said, it doesn't take a lot of equipment and capex to do that for smartwatch. Another application that's interesting is the augmented reality and mixed reality, and by extension also the HUDs, the head-up displays in automotive. So first, make sure we understand the difference with virtual reality. In virtual reality, the user is completely, I would say, sheltered, visually sheltered from the outside world, and wearing that head-mounted device, and all you see is the computer-generated image. In augmented and mixed reality, you're still seeing the real environment, and you have a computer-generated content that is overlaid on top of the real world. So what that means is that the display, the brightness of this overlaid image needs to be high enough to compete with the ambient light. And it's especially critical in outdoor applications or in bright environment. So that means that you have a very high brightness requirement for those displays, and it's compounded by the fact that since the display cannot be physically positioned in front of your eyes because they cannot block your field of view. Displays are typically on the side or on the top of the head-mounted device, and you have an optics that's going to project, or you can use waveguides to superimpose the image onto that shield, semi-transparent shield that you see on the front of the device. And those optics also have a fairly low efficiency, so you're losing a lot of light, a lot of photons here. So the requirements for those micro displays in those applications, in terms of brightness, we're talking probably 10,000 nits, maybe up to 50,000 nits, and I've heard even higher numbers. And today we believe that micro LED is really the only technology that could deliver that kind of brightness while still delivering efficient power consumption and in a form factor that is compatible with the application. So probably a very strong opportunity for differentiation to micro LED. In terms of the technology, those are micro displays, very high pixel density. So it's still possible to do it with a transfer pick and place process, as I described earlier. But the other avenue that's explored by many companies, we have Lumiode or the Leti Research Center in France, are working more on what I call monolithic integration with a CMOS circuit. So the idea here is to transfer the full display, the full array, and hybridize that on CMOS or grow the transistor structure on top of the display. In terms of cost, we believe that those applications initially will be driven more by enterprise rather than the consumer market. So there's a little bit more tolerance price-wise, a little bit more headroom. Let's say you cannot be orders of magnitude more expensive than the incumbent technologies, which are essentially a micro OLED displays or LCOS, liquid crystal on silicon. In terms of supply chain, here again, you have something that's fairly low volume, so fairly low capex, doesn't take a lot of MOCVDs, and we think that this is probably the only application where we believe that it could be addressed by a smaller company or a well-funded startup that could bring the pieces together by outsourcing some parts and doing some internally, but could probably have enough leverage to come up with the full supply chain and be able to manufacture those displays. So what's happening in a short term? Again, without getting into too much detail in our crystal ball, we think the technology is not completely ready yet. From all the interviews we've conducted, we believe that there's still a lot of issues to be ironed out. Each company has made progress in different areas, but so we see probably at least another year of development, and then you can start thinking about setting up the supply chain, so building all those manufacturing equipment, dedicated equipment, that again, most of them are not available off the shelves. And then you can maybe finally ramp up. So long story short, we really don't see the first high volume consumer product hitting the market before at least 2019. And I understand that in that regard we are much more conservative than some of our colleagues, some other analysts. But so far this is how we see things. And then if this first application is successful, it will help maturing the supply chain and ironing up all the latest kinks and problems, and probably help set the stage for other applications. Second scenario is we could imagine that in the end some of those technical challenges that are mentioned might not be solvable, at least not in a very cost-efficient way. In that case, we might see micro-LED maybe limited to some niche products, but high added value products, areas where the micro-LED performance are very highly differentiating, or where micro-LED would be the only technology delivering the required performance. So that's another scenario, and then we can still envision the catastrophic scenario where really the problem cannot be solved in a cost-efficient way, and everything crash and burns, and there is no micro-LED display. That's unfortunately a fate that many of the promising quote-unquote display technologies have encountered in the past. So my conclusion here is that micro-LED is inherently a more complex technology than OLED and LCD, but there are a lot of smart people working on solving those problems, and I'm actually fairly optimistic that they will be successful. I really don't see micro-LED completely displacing OLED and LCD, but they could definitely end up taking a dominant place in some markets where they have very, very strong advantage. I mentioned wearable, augmented reality, mixed reality, head-up displays. And for a variety of other consumer markets, could be smartphone. Although smartphone is a very difficult nut to crack for micro-LED, but tablets, laptops, even TV. Micro-LED could definitely compete on a very high end, because they will remain more expensive, for example, than LCD. But they could compete on a very high end with OLED. So this concludes my talk. Again, remember you that we have this much more thorough analysis in our latest report. And with that, I'm going to hand the microphone back to Camille.
Yes, thank you. Thank you very much, Eric, and thank you for this relevant and very interesting information you shared with us. So now it's time. We have a few minutes to go on the Q&A session. So we'll try to answer as many questions today as time permits and follow up via email on the remaining questions. So the first question, Eric, would be this one. In the report flyer related to this topic, you seem pretty bullish on adoption in cell phones, and what makes you so optimistic?
Interesting question. So it's actually a topic I was discussing recently with the OLED Association. I didn't discuss smartphone today. To me, they're really the most challenging application, I think, for micro-LEDs, because you have the same number, basically, same number of pixels as in a TV, which means potentially the same epitaxy LED cost. But the price target is way lower, obviously. So to make that happen, to make micro-LED cost competitive, you need to be able to do it with very small LED chips, probably less than 5 microns and probably even 3 microns or less. And as I discussed earlier, this increases the challenge in terms of efficiencies, but also makes the transfer process even more difficult. Handling LED chips less than 10 micron is very difficult. So I think all the challenges are somehow compounded for smartphone. Then you also have the supply chain issue, because if you're Apple, for example, and you want to start making a micro LED display for your cell phone, you need to set up a supply chain with a manufacturing run rate of probably more than 20 million units per month. So who's going to take the risk with you? And so it's also challenging on the supply chain side. So clearly the smartphone is a long shot, but we're not saying it's impossible. And we actually talk to companies that are specifically working on this problem. We know that some cell phone OEMs are currently building prototypes, and we know that some startups are working specifically on this market. So that's the reason why we still have some adoption in smartphone in our most aggressive scenarios. So the question was relating to the graph that we have on the flyer advertising this report, and the graph on this flyer is the graph for our most aggressive scenario. And indeed, we didn't want to rule out smartphones again, because it's not impossible, it's doable, but it's a long shot. And to be more specific, so I don't have the graph right now with me, but to be more specific, the underlying assumption in this scenario where we have smartphone adoption, the underlying assumption, of course, is that Apple would be the first adopter, which is why you see the volume going from 0 to 200 million units, give or take, in a short time span, or over two or 3 years. Other scenarios are possible, of course. For example, a tier 2 cell phone OEM might decide to use micro-LED just in some low volume, high margin phones. In that case, the challenge on the supply chains are different.
Okay, thank you very much. It might be a little bit short in terms of time to have a second question. I'm sorry about that, Eric. So for the people who did send and ask questions, so Eric will get back to you within an email within the next few days, so don't worry about that. And within the next 24 hours, you will receive an email that will include the recorded session, so you will be able to listen it again. And feel free to share the presentation with the person that can benefit from the information, and find all of our analysis and reports on imacronews.com. Once again, thank you for joining us today. Do not hesitate to contact us if you have any additional questions, and you can find your appropriate contact on the last slide of the presentation. Thank you, Eric, once again, and have a good day. Bye.
Thank you.